Did you know that air conditioning alone can account for up to 40 to 50% of a building's total energy consumption? This applies across commercial buildings, data centers, hospitals, hotels, warehouses, and schools. These systems run almost continuously, making them one of the largest drivers of operating cost. But over time, performance quietly declines due to aging equipment, coil degradation, and internal inefficiencies. This leads to unnecessary energy wastage, higher electricity bills, and increased system stress. That's why improving air conditioning efficiency is one of the most effective ways to reduce building energy consumption. Start with understanding where energy is being lost. Inside a refrigeration circuit, the refrigerant is compressed under high pressure by the compressor and flows in the refrigerant pipe. Regularly, the compressor oil enters the refrigerant pipe and circulates with the refrigerant. Minute oil droplets separate from the flow and begin wetting the inner wall through coalescence. This forms a continuous insulating film that adheres along the pipe, increasing thermal resistance and reducing the heat transfer coefficient. The heat is not efficiently dissipated from the refrigerant, resulting in inefficient condensation of the refrigerant. Consequently, the system refrigeration efficiency drops and energy consumption rises, trying to cope with the air conditioning demand. It is thus crucial to remove this buildup and prevent it from happening again. Outside the refrigerant copper pipes are the aluminum fins that help the heat dissipation. They are not spared from aging and damage too. The air-cooled chillers and condenser units operate fully exposed to outdoor conditions. Solar heat, rain, and humidity continuously act on the coil surfaces. This constant environmental assault gradually degrades the metal components, leading to corrosion, reduced efficiency, and serious, costly premature equipment failure. Without proper protection, these critical systems face an ongoing battle against the elements that can compromise their performance and lifespan. From commercial buildings, to hospitals, to data centers powering the digital world, cooling systems play a crucial role for the building and the infrastructures. And at the heart of most of these systems is water. Water has been the default heat transfer fluid for decades, especially from the chillers to the air handling units or the cooling coils in the HVAC systems. It's simple, it's familiar, and it works. It is increasingly used for direct cooling of servers and IT equipment via the cooling distribution units. But here's the truth most people don't realize. Water is also one of the biggest limitations to energy efficiency in modern cooling systems. Every cooling system depends on one critical function: the ability to move heat efficiently. Heat must be absorbed, transported, and transferred out. And this entire process depends heavily on the fluid inside the system. But water thermal conductivity is limited. This means heat cannot move through it fast enough, especially under high-demand conditions like data centers or fully occupied buildings. So heat exchangers become less effective. Cooling coils remove heat more slowly, and chillers must work harder to compensate. This leads to a hidden but critical effect: longer compressor runtime. Instead of reaching the desired temperature quickly, the system runs longer cycles. More electricity is consumed, more energy is wasted. But the limitation doesn't stop there. Inside every pipe and heat exchanger, water forms a thermal boundary layer, a thin, stagnant layer along the surface. This layer acts like insulation. It slows down heat transfer, right where heat exchange matters the most. Even in a perfectly clean system, this resistance exists. Then comes real-world operation. Water is never truly pure. Over time, minerals, impurities, and particles begin to accumulate. They form scale on heat exchanger surfaces, and even a very thin layer of scale can significantly reduce heat transfer efficiency. At the same time, water interacts chemically with metal surfaces. This leads to corrosion. Pipes and coils begin to degrade. Internal surfaces become rougher. Flow becomes less efficient, and heat transfer declines even further. Water also creates the perfect environment for biological growth. Bacteria, algae, and biofilm begin to develop inside the system. These biological layers act as thermal insulation. They block heat transfer, restrict flow, and increase maintenance requirements. To control these issues, systems rely on chemical treatment, filtration, and constant monitoring. But this introduces another challenge: higher operational complexity and cost. And in low-temperature applications, water freezes. To prevent freezing, additives like glycol are introduced. But this creates a trade-off: reduced heat transfer performance and higher pumping energy. So when we step back and look at the full picture, water introduces multiple layers of inefficiency, limited heat transfer thermal resistance, scaling and fouling, corrosion and degradation, biological growth, operational constraints, and the result? Cooling systems that are constantly compensating with their efficiencies, running longer than necessary, consuming more energy than required, operating below their true potential. This applies across HVAC systems, and even more critically in data centers, where cooling efficiency directly impacts operational cost and sustainability. So the real question is not just about improving chillers or upgrading controls. It is about something more fundamental, the transfer fluid inside. So if the limitation lies in the fluid, what if we change the fluid itself? So you have systems of chillers providing your building the comfort of cooling. You are enjoying the cool. But did you know that most chiller systems today are still operating like it's 20 years ago? Fixed set points, fixed schedules, and manual adjustments based on guesswork. But buildings don't behave that way. Occupancy changes by the minute. Weather shifts throughout the day. Heat loads fluctuate constantly, yet the chiller keeps running at a fixed strategy, regardless of actual demand. So what happens? Overcooling, excessive compressor runtime, and energy being consumed when it's simply not needed. To avoid complaints, operators often add safety buffers, cooling more than required, just to be safe. But this creates a hidden problem. The system is no longer optimized for reality, it's optimized for fear of discomfort, and that's where energy waste begins. As buildings become smarter and energy costs continue to rise, the future of cooling can no longer depend on aged HVAC systems and outdated efficiency. Because hidden inside every HVAC system, oil fouling quietly restricts heat transfer. Corroded coils slowly weaken cooling performance. Plain water reaches the limits of thermal conductivity, and fixed operating settings continue consuming energy, even when the demand simply is not there. These inefficiencies are often invisible, but over time, they become one of the largest sources of wasted energy in modern buildings. The future of sustainability is not just about producing more energy, it is about eliminating energy losses that already exist. A new generation of solutions to restore the HVAC systems, to enhance the heat transfer, and intelligent HVAC optimization are now emerging, where heat transfer becomes more efficient, where cooling systems respond dynamically to real building demand, where AI continuously learns, analyzes, and optimizes, and where every component works together as one intelligent ecosystem. The efficiency of the HVAC systems can be increased without having to replace them. Smarter heat transfer, smarter cooling, smarter energy usage, achieving the most sustainable energy in HVAC systems. Subscribe to this channel to stay informed of the smart solutions to improve the energy efficiencies of HVAC systems.